All right, so this is lesson 2 of related rates. Example 1. A water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. All right, so the first thing we'd like to do is to draw a picture to represent this. So we know we have a water tank and we know that it is represented by an inverted circular cone. So we're going to draw that. So that there is our water tank. It has inside of it water. We also know that it has a base radius of 2 meters. So this distance here is 2 meters. And it has a height of 4 meters. So from here to here is 4 meters. We know that water is being pumped into the tank. So we see here water coming in to the tank. And it's been coming in at a rate of 2 cubic meters per minute. So water being pumped in changes the volume. So we know that dV dt, or the change in volume, is equal to 2 cubic meters per minute. The question is, find the rate at which the water level is rising. So we want to know the height of the water and how fast that's changing with respect to time. Note here, this is the radius of the water at the level. And we would like to find dH dt when the water is 3 meters deep. So when the height is 3. All right, so now that we've pulled all the information we need from the word problem, we're going to try to tackle it. We see here that our problem has the derivative of volume and derivative of height. That means we need an equation that finds the volume of a circular cone. We know that volume for a cone is given by the formula V equals 1/3 pi r squared times height. In this case, we can see that we would like to find dH dt, and we have dV dt. If we currently differentiate this function, we have a problem because this has r squared and we do not know dr dt. So what we'd like to do is to create a version of this equation that only has v and h. So we're going to jump backwards to some of our high school geometry knowledge. If we look over at our inverted cone, we'll notice that the water level forms almost like a triangle, right? And that the cone itself forms another triangle. When looking closely at these two triangles, we can see that our yellow triangle and our purple triangle are similar. And we know from high school geometry that similar triangles form proportional relationships. That is, we know that the radius of the yellow triangle over the radius of the purple is equal to the height of the yellow over the height of the purple. Now what this does is it gives us a relationship between r and h. So we could then say that r is equal to 2 times h over 4, or that r is equal to h over 2. Now we're going to use this information to modify this equation so that we have an equation for volume that only has v and h. So we have v is equal to 1/3 pi, but instead of radius, we're going to put height over 2 squared times height. And simplifying this, we get 1/3 pi times height squared over 4, because 2 squared is 4, times height. And then simplifying once again, volume is equal to, instead of 1/3 now, let's say 1/12, because 3 times 4. So 1/12 pi times h cubed, because h squared times h is h cubed. Now we can differentiate. The derivative of the volume with respect to time is dV dt. The derivative of the right-hand side is really just the derivative of h cubed because 1/12 pi is a constant. So we're going to get 3h squared. So 3 times 1/12 is 1/4. So 1/4 pi h squared. Okay, dH dt. Now we're going to go ahead and we're going to plug in everything we know, right? So when h is 3, what does this become? Well, dV dt is 2. So we have 2 is equal to 1/4 pi, the height is 3, and dH dt is unknown. So we get 2 is equal to 3 squared is 9, so 9/4 pi times dh dt. We'd like to solve this for dh dt, so we're going to divide both sides by 9/4 pi. So dh dt is 2 over 9/4 pi. We don't like the fraction within a fraction, so by multiplying both the numerator and denominator by 4, we can simplify this. So we get 8 over 9 pi, and this is the change in height. So the units is meters per second. We would say then, the rate at which the water level is rising when the water is 3 meters deep is 8 over 9 pi meters per second. All right, let's take a look at example 2. Car A is traveling due west at 50 miles an hour. Car B is traveling due north at 60 miles an hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 3/10 of a mile and car B is 4/10 of a mile from the intersection? Right. The first thing we're going to do is we're going to draw the intersection. And then we're going to place the cars appropriately. So car A is going due west towards the intersection. So we're going to place car A right here. And he's going this way. And car B is traveling due north towards the intersection. So we're going to place car B right here. And he's going north. Now we do know how fast they're going. We know car A, we're going to call this distance here from the intersection X, and this distance here from car B and the intersection Y. So we're going to say dx dt is decreasing by 50 miles an hour. So dx dt is negative 50. And we're going to say dy dt is also decreasing. So negative 60 miles an hour. Because the distance from the intersection Y and the distance from the intersection X is getting smaller, we'll use these rates as negatives. Okay? And then we're going to say that the distance between the two cars is given by this line here, and we're going to call that Z. Now note here, this forms a right triangle. Okay? We would like to find the rate at which the cars are approaching. So that is, we want to find dz dt when x is 3/10 of a mile and y is 4/10 of a mile. All right, so we need an equation that relates the x, y, and z. Now, seeing as this is a right triangle, we know the relationship is based on the Pythagorean theorem. So we know that x squared plus y squared is equal to z squared. We'll go ahead and differentiate. We get 2x dx dt plus 2y dy dt equals 2z dz dt. Now we'd like to solve this equation for dz dt, so we'll divide both sides by 2z. And we get that dz dt is equal to 2x dx dt plus 2y dy dt all over 2z. Now we're going to be evaluating this. So dz dt when x is 0.3 and when y is 0.4 is equal to 2 times 0.3 times negative 50 plus 2 times 0.4 times negative 60 all over 2 times z. Now the question is, what is z? Well, if I know x and I know y, I know z, right? So we have here, I'm just going to use a quick calculator, 0.3 squared plus, 0.3 squared plus 0.4 squared equals 0.25 square root, so we can see that z is 0.5. Going ahead and calculating this, 2 times 0.3 is 0.6, 0.6 times negative 50 is negative 30, 2 times 0.4 is 0.8, times negative 60 is negative 48. Divided by 2 times 1/2 is 1. Negative 30 and negative 48 makes negative 78. And it's negative 78 miles per hour. And so we would say then the cars are approaching each other at 78 miles an hour when car A is 3/10 of a mile and car B is 4/10 of a mile from the intersection. All right, the final example. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and rotates to keep its focus on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay, so we're going to start with our drawing. So we have our path, we have our man. The searchlight's down here, and it's following him. From the path, it is 20 feet. And it follows him. He is walking at a speed of 4 feet per second. So we're going to call the distance from the shortest distance to the man, we're going to call it x. And we're going to say then that the change in x with respect to time is his speed, is 4 feet per second. And we know this distance is 20 because it says. And this rotates to keep his focus on the man. At what rate is the searchlight rotating? So we would like to measure the rotation, that is, the angle at which it moves. So we would like to find d theta dt when x is 15. So we need an equation that relates theta and x and 20. So using our trigonometry knowledge, we know that theta is opposite x and adjacent to 20. So we get that tangent of theta is equal to x over 20. Differentiating both sides, we get secant squared theta d theta dt is equal to, and the derivative of x is 1 dx dt, but this is 1 over 20 times the derivative of x, so it's 1 over 20 dx dt. Okay, we would like to solve this equation for d theta dt, so we're going to divide both sides by secant squared t. So we get 1 over 20, 1 over secant squared theta, dx dt. Now note here, 1 divided by secant squared theta is mathematically equivalent to cosine squared theta. So we have 1 over 20 cosine squared theta dx dt. Now we would like to evaluate this. We want d theta dt when x is 15. That is 1 over 20 times cosine squared theta times dx dt, which is 4. Now this part confuses folks because we're evaluating at x being 15, but our function here takes in theta. So the question is, what does it mean for x to be 15? Well, when x is 15, our triangle looks like this: 20, 15, and theta. The question is what is cosine, right? So cosine of theta is what? Well, if we have the legs of the triangle, we can write the hypotenuse. So we know 20 squared plus 15 squared is equal to our missing side squared. So we have 400 plus 225 is 625. If we square root that, we get that the missing side is 25. So cosine of theta, which is adjacent over hypotenuse, is 20 over 25, or 4/5. Therefore, this is 4/5 squared. So we have 1 over 20, 16 over 25, times 4, which becomes 64 over 125, which, let me try that again, becomes 64 over 500, which reduces to 16 over 125 degrees per second. And done.